Alrighty, here we go with the recap of what we did today. We talked about the torque, and torque is the ability of a force when a force is applied to an object that has a fixed pivoting point, like in here, we have this bar that is able to rotate relative to this pivot point on the stand, and if a force is applied anywhere but that axis of rotation, it will create a torque. Depending upon how far from the axis of rotation and at what angle that force is applied, torque will be different. In this particular example, all three forces, force of gravity from 40 grams, force of gravity from 20 grams, and force of gravity from another 20 grams, they are all applied in different spots. And if I were to be true to showing the actual free body diagrams, then the 40-gram force, which is 40 centimeters away, versus the two 20-gram forces, because the mass is twice as big, then this force of gravity should be twice as long as these two. Now, look at that. Even though the forces are equal, the two forces on the right would be 0.02 times 9.8 plus another 0.02 times 9.8. Together, they add up to the same as 0.04 for 40 grams times 9.8. However, the system won't be balanced because this right here is hanging too close. It's not hanging 40 centimeters away from the fulcrum or from the pivoting point. It's hanging only 20 centimeters away. And that is why this system is not going to be balanced. Because of this greater lever arm, the force on the left is going to create a greater counterclockwise torque than the two forces. We have a clockwise torque and another clockwise torque. And those two, that one I would multiply by 0.2 for 20 centimeters, and this one I would multiply by 0.4 for 40 centimeters away from the fulcrum. That torque is 0.4 times force of gravity. Counterclockwise torque in this case is greater than clockwise torque. In question 2, we were tasked with figuring out what kind of mass we can hang out at this point in order for the system to be balanced. So when we're talking about static equilibrium, we're talking about forces being balanced and torques being balanced. So we are balancing the two torques. Counterclockwise torque, the CCW, counterclockwise, comes from 50 grams. So this would be mass 1, which is right here, mass 1, times G times 0.4 in meters. So torque is measured in newtons times meters. And then clockwise torque is coming from this unknown weight right here. And that would be mass 2, or I'm going to say mass question mark, times G. And that lever arm is just 0.2. They should be equal to each other. So if I set them equal to each other, then I can cancel G. And I get 0.4 of mass 1 should be equal to 0.2 of mass question mark. Then I can divide by 0.2 and end up with 2 mass 1 equals question mark. So if I want to balance this, I have to hang 100 grams over here in order for the system to be balanced, in order for the clockwise torque to be balanced by counterclockwise torque or vice versa. So I can say that clockwise torque plus counterclockwise torque equals 0. So their magnitudes are the same, and counterclockwise is considered positive, clockwise is considered negative. So when we add them together, they would add up to 0, and your total net torque, you're welcome to use this, or you can say that. Usually this is easier to see. So tau stands for torque. It's like T, but you get a little bit of a cap. That's your tau. This is torque, and it's measured in newtons times meters. Number 3 is a little more complicated, and I'll show you in the next video how to solve that.